Hello, everyone. Welcome to this first appointment of 2026 of the 40 under 40 lecture series on combustion. Happy New Year, everyone. And then we have the pleasure to host Dr. Fabian Hampp from the University of Stuttgart in Germany. Dr. Hampp is the Military Research Group leader at the Institute of Combustion Technology for Aerospace Engineering at the University of Stuttgart. He obtained his PhD at Imperial College London with Professor Lindsted, and for this PhD was followed by a postdoc on turbulence chemical interaction to suppress pollutant formation in out-ignition influenced combustion. From 2019 to 2021, he was involved in at the DLR, Stuttgart, to advance fuel flexible injection and compact liquid fuel combustors, and he received the Sagden Prize and the William George Prize. His research targets clean fuel flexible combustion of conventional and future fuels by combining additive manufacturing, enabled injection and mixing systems with also deep learning augmented optical diagnostics to resolve turbulence chemistry phase interactions and quantify emission pathways, and supporting the development of low emission combustion strategies. Fabian, thank you very much for accepting our invitation, and I leave you the virtual floor.
Thank you very much for the introduction. I will start the presentation, hopefully. Can you see the correct screen? So
yes,
this one and also the laser pointer?
Yeah.
Okay, perfect. Thank you very much. So today I will focus a talk on the way we use additive manufacturing to enable clean and fuel flexible combustion. And I would also address what opportunities arise with that and what emerging challenges come with that. New manufacturing technology is not so new anymore, but entering really the combustion side. I want to motivate this talk from two angles. First of all, of course, from the combustion side, in particular now, or this slide here, in terms of aviation emission. Aviation is responsible for around 5% of the anthropogenic climate change, with the sector projected to grow around 4%. This is also one of the hardest sectors to decarbonize, and sustainable aviation fuels offer here the highest CO2 reduction potential. It's not only doesn't only have the potential to reduce CO2 emissions, but also with the fuel design, we can affect the combustion efficiency, or in particular the soot formation. So when we, for example, may reduce the aromatic content in the fuel, that can lead to, or can offer us a soot reduction potential in the end. This is quite important because, and it's quite well known, that non-CO2 emissions basically exceed the CO2 climate impact in aviation, but is also affecting or impairing local air quality and increases carcinogenic exposure. When we use SAF, also hydrogen, that still leads to contrail formation, also NOx formation. So it doesn't really make, so just using SAFs doesn't make aviation climate neutral. And in order to mitigate, in particular NOx, we need technology advancements. Also, NOx formation is not strongly sensitive to the SAF composition. So when you remove, for example, the aromatic content, the temperature is still high, you still form thermal NOx and so on. Same holds for hydrogen. So also for reducing NOx, we really need technological innovations here. When we change the chemical composition, we of course also inherently change the physical fuel properties. And here I show you spray me scattering images at realistic conditions. And here down here you have HEFA-A, and this fuel has twice the viscosity of Jet A1, for example. And you can see by the amount of me scattering in the combustion chamber that you have a deeper penetration of the fuel into combustion chamber, and this positioning it into regions where you presumably don't want it. And this is deteriorating the mixture homogeneity and impairs the non-CO2 emission reduction potential. The second side I want to motivate is the use of additive manufacturing in combustion systems, in particular because modern combustion systems are often additively manufactured. For example, here, the Siemens SGT 600 or 800, or also the CFM or GE LEAP engine fuel nozzle down here. Motivation is often here a reduction in part number, weight, and also in manufacturing time. But additive manufacturing can go significantly further. So here I show you an image of a multi-material printing process. I borrowed this from Fraunhofer, where they combined the printing of copper with stainless steel or with steel to combine enhanced heat transfer and also structural integrity. This can go even further up to like in situ alloy generation. So basically you fuse powder, you blend powders or you create new powders and then really create in the printing process new alloys tailored for their functionality in the position where you place them. Additive manufacturing is also heavily used for repair of in-service components. Like here, this is then more direct energy deposition. We basically rebuild turbine plates or compressor plates to fix them, basically. One big project I want to highlight here is also, or one big area is function integration, and particularly the DFG-funded SPP 2419 HiCam project that is being run by Heinz Pitsch, and we have a sub-project in that. And this overall project focuses on the use of additive manufacturing for hydrogen carriers. And there are a wide range of projects focusing on performance gains via geometric optimization. Our project is also focusing on utilizing the enhanced surface roughness to activate ammonia cracking. But what I want to focus today is basically the use of additive manufacturing to enhance mixture homogenization, fuel flexibility, and also mitigate emissions. The research field we work in is a bit wider, so we focus on, in general, turbulent reacting multi-phase flows. We want to realize clean and fuel flexible combustion, ranging from hydrogen, ammonia with particular focus on liquid fuels. We advance fundamental understanding and use advanced manufacturing technologies to optimize injector hardware, design flow components to allow us to decouple physical processes better, to basically end up with cleaner combustion processes. For this purpose, we use a lot of laser-based diagnostics that produces a lot of data, of course. And in order to post-process these data or advance this post-processing of the data, we develop deep learning-based methods to support the data analysis of image-based diagnostics predominantly. But the focus of today's talk is basically on this additive manufacturing side, the way we use it in order to optimize combustion systems. So before we deep dive into the content, I want to introduce quickly additive manufacturing and then focus on the experimental work we do and show you some examples of injection systems that we have developed over the past. And then in the end, I will highlight where I see the emerging challenges for the use when we use AM in combination with combustion. Good. So here, I let this video quickly play. You see the scanning process of a laser and solidifying material. Yes, it stopped. Good. So the process we use is powder bed fusion. The way this works is you have a powder bed here. You recoat or you place basically a thin layer of powder here. Then you have a laser that solidifies, that melts the material. It's basically a micro welding process. So wherever the laser exposes the material, it solidifies. Then the build plate lowers and the next layer of powder is being placed and the laser starts again. And then again, I need to quickly, I can't restart the video unless I turn off the laser pointer. You see this here, the laser scanning basically the powder where it's supposed to solidify, and that creates solid structures. Good. There are a couple of inherent problems with that, in particular when it comes to smaller scale structures. And the inaccuracies I'm going to talk about now is always assuming that you already have a good additive manufacturing process, so stable melt pool. So for example, for the surface roughness, because you have this layer-based approach, you end up with some sort of staircasing effect if you have inclined surfaces. This is visible here slightly, and it's better visible here. You see these larger structures, this waviness of this contour. That's basically due to this layer-built approach. On top of that, you have partially melted particles, so partially fused powder material that is sticking to the wall, enhancing the surface roughness. The second part is tolerances. So you have a certain laser spot size that creates the melt pool, and that is dictating basically the accuracy you can achieve for that. You can also have, or the tolerance can also be influenced by irregular or insufficient heat transfer away out of this melt pool, or if you have unsupported structures, sagging of material, like you can see here, it's lowering a little bit, it's not holding the nominal contour. And why is this important? So I just want to give you a rough idea of the precisions we talk about in additive manufacturing powder-based fusion. So solid structures, in order to create a wall, you need to like 2 to 4 melt pool widths roughly. And this leads to minimum wall thickness, usually above 500 micrometer. So these numbers are really just to give you an idea of the range we are talking about. And the channels, for channels or internal structures, here the quality or the accuracy of internal structures is heavily dependent on the build orientation. So vertical holes, you probably get a much better quality of a vertical hole in comparison to a horizontal channel due to this sagging and unsupporting these structures. Typically, the dimensions also around bigger than 500 micrometer, and every channel that is bigger, or especially horizontal channel that is bigger than 5 to 10 millimeter needs support typically. When we now talk about injection systems, this can become problematic because usually you have multiple injection orifices that are fed out of a single plenum. You have complex internal structures that you can't post-process, you can't machine them or sandblast them, and you have high flow velocities through these orifices, making it sensitive to the dimensions. And now on the other side, you have the additive manufacturing. And let's say we have tolerances of 20 to 100 micrometer. You have a support-free print, which makes the surface quality of overhanging structures worse. And you have a surface roughness that is somewhat dependent on the powder size distribution. And in particular, I want to highlight here the peak roughness in powder bed fusion processes. Even if it's optimized, the peak surface roughness can easily reach like 50 to 70, 80 micrometer. That's not uncommon, okay? And then when you have an angled surface, on top of the surface roughness, you also have the staircasing effect with the layer height, and typical layer heights are between 20 or 40 micrometer, depending on the optimization of the build process. They can also be higher. When we now have an injection system or an orifice of 200 micrometer with a tolerance of 20 micrometer up and down, that leads to an area uncertainty of 50%. And that is that's problematic because, of course, if you have one pressure in the plenum, and now we have a variance of the injection orifice that vary 50% in area, that leads to significant differences in fuel being ejected through these orifices. And that inherently impairs mixture stratification. It leads to elevated non-CO2 emissions and is challenging to reproduce because the next part, presumably these inaccuracies will be distributed differently. The way we work around this is by functionalizing defects to create some sort of tailored permeability. In order to explain this, I need to deep dive quickly in the way additive manufacturing, these powder bed fusion processes work. So you have these layers, so these solid lines represent the laser, the melt paths, the melt pool tracks basically. And in the next layer, you rotate these laser lines. Typically, you rotate the laser lines by 67 degrees in order to get the best isotropic material properties possible. but you can detune this angle to 45 degrees or 90 degrees, and then you end up with some sort of structure in this build layout. The second parameter that we vary a lot is the hatching distance. So that's the distance between the laser path lines, basically. Typically, if you want to have a solidified part, they overlap, and you create a solid part. But when you now detune that and open the space between them, you create gaps. And in combination with hash distance and rotation, you can basically tailor the permeability vector. You can direct it. For this, I show you quickly a few micro CT images. So here you have a scan strategy of 67-degree rotation and here of 45-degree with a hatch distance of 5 laser spot diameters. And you can already see by the interconnected colored regions here, when we have a 45-degree rotation, the connected pores are much, much larger in comparison to the 67-degree approach. And when we then increase the hatch distance, we can basically create really large interconnected pores, and that creates permeability, basically. And that permeability is directed in these structured approaches here. And this is what we use later on in designing the new injection systems. Okay, let's go to more the combustion side. I will introduce the burner framework and the experimental setup next. So we typically use jet stabilized combustion systems, highly turbulent jet flames, approaching the flow conditions of high momentum jet stabilized combustion systems. The way this works is you have air penetrating at high velocity into the combustion chamber. The combustion nozzles are placed off-centered. That creates space for a large internal recirculation zone that transports heat and radicals back into the shear layer here, and it's being entrained into the shear layer, and that leads to some sort of out-ignition influenced flame stabilization. We choose this combustion concept due to wide operational range and also wide fuel flexibility with simultaneously low emissions. So here you see Jet A1 flame for varying equivalence ratio, and here you see a hydrogen or natural gas enriched hydrogen flame or methane enriched hydrogen flame. And the flame stability is very comparable. The flames are always lifted, and you can operate the same burner basically from hydrogen to heating oil and kerosene. When it comes to the injection systems for these type of combustors, these are rather challenging because you need to split up the fuel mass flow rate in the large number of nozzles. So instead of having one injection system for given thermal power, you now have 12 or even more injection systems, and that makes it rather challenging to produce these. In terms of liquid fuels, we use jet and cross flow injectors for either as a direct injection system or as pre-filming system or air blast systems. And for gaseous fuels, we typically use jet and co-flow or jet and cross flow injection systems. These are quite common. Now they're also mostly additively manufactured, but there's nothing extraordinary around of these, except for maybe the geometry. And we use now additive manufacturing in this micro print approach to develop new types of injection systems with the motivation to enhance fuel flexibility, load flexibility, and also scalability. With this, I would now like to introduce the burner configuration. As I said, it's a turbulent jet flame. In our burner is a piloted turbulent jet flame. We have the preheated combustion air coming up here in this channel. We have in green the fuel supply lens. On top mounted an injector. Here you have an air blast wall installed in blue surrounding the injector, and then in red you have the combustor nozzle. Down here you have a porous plate that anchors the pilot flame that is then surrounded by shield air here. Okay, I think this will become again clearer when I show you some images. The flow conditions we operate this is typically between 30 up to 160 meter per second bulk velocity. The temperature of the air varies between 300 and 800 Kelvin. The fuel is supplied by nitrogen pressurized piston cylinders that makes it fluctuation free. And the fuel supply lens is water cooled up to the point of here to maintain the physical fuel properties constant. And the fuel mass flow rate is can be varied for over a wide range from, let's say, 0.05 grams per second to 1.2, although we can also go higher and somewhat smaller here as well. Good. Before I start with the way we use additive manufacturing concepts in this type of burner systems, I would like to introduce or explain the overall injection system. So we have the pressure swirl injector here that creates a hollow cone spray and pre-films a wall. This wall film is then driven up by a co-flow air going past here, and that's meeting an atomization air here at the air blast edge, and the flow rates are adjusted so that you have high shear leading to this air blast atomization. It's a very modular design, so we can exchange the injection system, we can vary the mixing length, so the distance between this edge and the combustor nozzle exit. We can vary the length of the film, and we can vary the air flow guiding system around these injection systems, and also upstream of that. In terms of diagnostics, give you a quick introduction to the baseline diagnostic system that we use. We use background illuminated shadowgraphy to quantify the primary atomization. We use three-phase Doppler interferometry to measure droplet size, statistics, and also droplet velocities. We measure high-speed and low-speed OH chemiluminescence to detect the flame position and flame anchoring process. And we measure NOx or exhaust gases with an emission probe. We also use more sophisticated laser setups from phosphorescence-based PRV to do thermographic measurements. We use laser-induced fluorescence for fuel vapor, OH, and soot precursors. We are in the process of setting up LRI, but this will take a little bit more time, and so on. But the current talk will focus on this kind of diagnostics that I've shown here. Good. Coming to our additive manufacturing playground, so now bringing it all together. The first part will focus on the way we use additive manufacturing for turbulence modulation via either fractal grids or low swirl concepts. Okay, so here we only alter we insert a component that changes the airflow around the injection systems. And the second part will then focus on the additively manufactured injection systems. So here, an injector that we call AM Flex injector, fully printed, and also in the last part, space filling injection systems. A quick disclaimer here, all additive manufacturing parts have been produced by the Institute for Machine Tools, IFW, at the University of Stuttgart, an institute that we collaborate widely with since a number of years now. And I now would like to start with these low swirl concepts to focus on spray stability. Okay. So, and the connection to the additive manufacturing here is the way we use these concepts now to enhance fundamental understanding in order to make these sprays more robust. Good. So we have a number of configurations manufactured. We have a pressure swirl injector here. We have this blue component. This is the one that is additively manufactured. That's also shown here. And now we vary the vane angles of only the inner vanes. So we swirl the inner air going past the injection systems, either in co-flow direction or in counterflow direction with respect to the pressure swirl spray. The swirl numbers are really low. They're below 0.3. Okay, so this is the objective here is just to stabilize the sprays. I quickly show you now the global spray and later on also flame patterns. And what you see here is in the straight vane case without swirl that the sprays are really opening up. You have a relatively large spray angle. The nominal spray angle here is 90 degrees. And when we now introduce low swirl in either direction, the the spray angle becomes much, much closer to the normal one, the design point, okay? Here is the flame response. So it's all the same operating condition that is listed up here. So jet velocity of 120 meter per second, pre-temperature of 650 Kelvin, same mass flow rate, and so on. And you can see, of course, when we introduce swirl, the flames become much shorter. But what is important to note here is that the swirl is so low, or so little, that there is no internal recirculation. So the droplets are not being transported back in the inside of this flow. It's all axially directed away from or downstream, basically. Good. And now I want to analyze this, or we wanted to analyze this a bit further, okay? So in the first thing I want to show you is a brush thickness. It's a gas-liquid interface brush thickness. So basically, we tracked this contour between the spray and the air and looked at the motion in physical space. And down here, and then we determined basically the 5 to 95% brush thickness of the statistical distribution. So here you see the brush thickness for the straight vane case in always left-hand side and right-hand side separated, and a top for co-flow swirling and a bottom for counter swirling with respect to the pressure swirl injector. There are a number of two main observations. So when we start increasing the swirl, the brush thickness becomes much thinner. That means this sheet is much more stable, it's much more fixed at one position or a narrow position, and also the open and the open and the closed symbols, they approach each other. They become the spray becomes much more symmetric. Okay. We looked at this further and also looked at the breaker point. So that's the final point of the interconnected liquid sheet, and then basically tracked this point in space. So again, here you have the co-swirling cases in the top row and the counter-swirling cases in the bottom row. The black lines or the black cases is the straight vane cases, is non-swirling, and then the colored parts are the swirling cases, separate into left side and right side. And what you see is that when we increase, or when you have swirl, the breaker point stability becomes much more fixed in space. Okay. And the distribution reduces a lot. And this is quite an important property because the breaker point in space basically dictates the droplet ejection velocity and therefore fuel placement, and therefore it strongly influences mixture stratification. Okay. Good. We also measured droplet size statistics on that, and very similar. Color coding always stays the same. Black is the straight vane case, and colored coded is the low swirl cases. When we start introducing low swirl, the droplet sizes decrease, but more importantly, the distribution of the droplet sizes and also number density becomes more symmetric, and the fuel distribution or the fuel penetration becomes radially broadened. Okay. And these are all attributes that basically are beneficial for mixture homogenization. Okay, and that in turn leads to reduced emissions or non-CO2 emissions. We varied this, of course, also in the operating parameters. So here we varied the jet velocity from 80, 120 to 160 meter per second at constant fuel mass flow rate. In the bottom row, we varied the fuel mass flow rate from 0.1, 0.3, 0.5 grams per second, constant jet velocity, and we basically seen that when we have low swirl around the injection systems, the breaker point stability becomes significantly more stable. With this understanding, we now basically recess the injector into the air blast wall and use this more symmetric, more stable spray to create a film. And with a more symmetric primary spray, I create a more symmetric or more homogeneous film that I then atomize. And this is directly reflected in the flame emitter. So what we've seen here down, the strong axial compression of the pressure swirl spray flames has been a bit mitigated is still compressing it, but not so strongly. We also measured droplet size. We see not a very strong effect in terms of droplet sizing down here. We have a bit broader radial distribution when we have low swirl, but what I really want to show you is the effect on the emissions, where we now have the low swirl cases in an airblast configuration. We really drop NOx emissions from up here to down here, and that is simply by having a more symmetric or a more homogeneous film on the airblast wall. So that has a big impact on the NOx emissions. I very briefly want to summarize this section. So basically, we've used additive manufacturing to create flow modulators to facilitate a systematic investigation of how low swirl influences atomization, spray stability, and so on, and thereby enhancing our understanding of turbulent spray interactions, and in the end, reduced non-CO2 emissions. Additive manufacturing has been a real game changer in this context because it allowed us to prototype a large number of different configurations for reasonable cost. And basically, these rather easy design or rather simple design variations come for free because the machine just takes the cut part and basically produces it, right? And you don't have to reprogram the CNC machine. It also helps you to reduce the modular designs. So because you can replace the entire component, you don't have to stack everything, and that eliminates a large number of assembly tolerances. And I strongly believe that assembly can have a strong effect on the accuracy that we produce in our experiments. We can enhance the flow engineering. It gives us more freedom to do stuff with our flow. It can improve the repeatability because of the reduction of assembly tolerances, and it can also improve the experimental quality. It doesn't have to, but it can. But in order to really benefit on this, so we have here a highly tailored additive manufacturing process, and with this we really achieved very fine edges that helped us, for example, to minimize flow separations and so on. Good. Coming to the second part, the way we use AM for designing new injection systems, and I want to start with this multi-fuel injection systems that we call AM Flex Injector. I will introduce it now, also the way we install it into the burner. So you have the same burner basically, but now the fuel is supplied from the outside here through this outside port instead of the central fuel supply lens. So, and here the fuel is basically, instead of sprayed onto the wall, we directly lay the fuel onto the wall, and then we still have the co-flow air and the atomization air that lead to this atomization, this air blast atomization up here. Here's the part in real, the way it looks like. So we have the fuel coming in here, so then being transitioned into this wall. We have the co-flow in the middle and the atomization air on the outside. And here, this shiny edge basically shows you the position of the slit. The slit is extremely small. It has a nominal diameter of 50 micrometer. And I will now show you some micro CT images of the accuracy or the inaccuracies of this additively manufactured part. Okay. These micro CT images have been conducted, or this measurements have been conducted at MIB at the University of Stuttgart. We have a really fine scanner, and now you can see basically the structural non-uniformities of this part. You see the waviness here. You see a lot of partially melted powder here and here. You have the wall, and this is the slit basically where the fuel later on comes through. And the nominal size is 50 micrometer, but you can see that this is far from perfect. We also measured this statistically, and we do have a mean of close to 50 micrometer, but the variance is really strong. The variance is like plus minus 15 micrometer. But you can't this is something you can't really change that. You have to live with it if you want to use this kind of manufacturing process for these kind of small structures. but it gives you a lot of flexibility as well. And I show you now the performance and later on explain why this has worked, or why we think this has worked. So we have, for example, slit injector S1 has a film length of 8 millimeter. Then we have S2 that has also 8 millimeter film length, but has micro speed bumps, 3 rows of like 40 micrometer height structures to homogenize the film. Then we have one with a swirler, and we have one with a longer film length, and so on. And we compare this with the conventional injection systems. The operational range is very similar to before. We have a flow velocity variation over a wide range. We can preheat the air temperature. We operate here in the first part still with Cherry 1. Later we expand the fuel matrix, and we have a wide range of liquid mass flow rates. I want to show you the way we characterize the sprays quickly. So we have here these shadowgraphy images, high resolution shadowgraphy images. Here you see the liquid film penetrating into the air. Here, this is the air blast edge. And then we employ our machine learning based detection that is, again, publicly available and can be used. And then we basically we detect these, the free film penetrating into the combustor. I hope this video shows a bit more fluently on your side. It's a bit lagging. And then with that, we basically calculate the free film penetration depth, for example. Okay. And we do this so here I show you first some instantaneous shadowgraphy images for a constant fuel mass flow rate at varying bulk velocity air bulk velocity from 20 to 90 meter per second. And then we analyze this statistically to measure the liquid penetration depth away from the combustor, from the air blast edge. And then with increasing air velocity, you see that the free film is penetrating significantly less into the combustion chamber, basically. We vary this also for fuel mass flow rate from 0.16 grams per second to 0.38 grams per second at constant velocity, air velocity. And we see that with increasing fuel mass flow rate, we penetrate deeper. The color coding is basically the area of the free film. But what is quite important to note is that we are reasonably well symmetric around the axis here, despite the inaccuracies we have with this injector. We also measured droplet size statistics. So here at top, this is axial droplet velocity, radial droplet velocity, and diameter. This is the 8 millimeter film variant. Then we have one with the speed bumps. We have the one with the swirler. And we have the conventional case. And what we see is that we don't see strong differences, maybe except for the swirler case where we have a radial velocity component. But the droplet sizes are really small. They're reasonably well distributed, actually symmetric, and so on. And this is actually good. This is what we want because it allows us allows homogeneous fuel placement. To complete the picture, I see I'm a bit short on time. I need to speed up even more. Sorry. This is a flame response. We have symmetric flames, and even under globally rich conditions, we don't observe much soot in these flames. Okay. We expand the fuel matrix now to Cherry-1, or we use Cherry-1, ethanol, methane, and hydrogen, and basically use an air blast injection concept for hydrogen. And I show you the flames for that. So we have here the Cherry-1 flame and the methane flame, and the flame anchoring process is reasonably similar for both types. Okay. And then on the right-hand side, I show you now the hydrogen flame. So here, this is more bulky and low position in the center. But this is also what we expect from a hydrogen type of combustion in this type of burner. This is very similar to the work of Petrial, where the flames are much more compressed into the center. Okay. And the reason why this has worked is we have used a liquid fuel injection system with an unconventional large fuel port that allowed us to decouple the injection process from the physical fuel properties. the atomization and mixing is purely driven by the airflow around this injection system and not by the properties of the injection system itself. And this process, this part, is very good for being produced by additive manufacturing and has been enabled by additive manufacturing. Good. The last injection system I will keep very short, but I want to show it because it's a combination of what we have done, like of all of it, what we have done. So it's these space filling injection systems. Here I show you an image, microscope image. We have these multitude of like 800 micrometer tubes. Inner diameter is 400 micrometers. You can see everywhere these partially fused powder material. And on top of these tubes, these are covered, these are enclosed with porous structures. Or they are, we have them fully as a normal tube with a lot of 250 micrometer holes. These holes are far from 250 micrometer, but there are so many, and not randomly, but they're quite well distributed, that the accuracies of these don't really affect the mixture homogeneity. So the design hypothesis behind these injection systems is that the mixing is driven by the spatial distribution and the airflow around this, and the high number of basically ports or orifices renders this insensitive towards the additive manufacturing tolerances. So we have produced a lot of these different injectors. Again, I apologize for the speed of this now. So we have a number of different injection systems that we can place as a fully premixed condition or direct injection or partially premixed configuration. And we measured the mixture quality with Schlieren. This is something I want to show you quickly. Or basically, I want to present you the result of that. So you have here the fully premixed case, here a non-premixed case with a tube injector, and here some of these additively manufactured micro injectors. And what the results have shown is that we managed to achieve a fully premixed criterion very quickly with like only 2-3 nozzle diameters for a wide range of operation conditions, and that we have decoupled the mixture formation process broadly from the fuel injection momentum and the fuel type. Okay, and that is very good for fuel flexibility because you at least have the same mixture homogeneity regardless of the fuel type you send through the injector. For further information, I would refer you to this publication here where we discuss this in detail. Last on this injector, quickly the flame response of that. These are partially cracked ammonia flames, where you see that the fully premixed case is basically closely anchored to the combustor nozzle, and the non-premixed case with the tube is lifted. And when we then use the additively manufactured injection systems in a direct injection configuration, we see these microstructures, but when then we recess the injector 4D, we approach very quickly the fully premixed conditions here. Good. Coming to the challenges. The obvious ones are manufacturing tolerances. So they can influence the flow distribution, and you should really take care of not to study an AM artifact when using that. In particular, when the dimensions become small. So we have to deal with very small dimensions, but it's something to keep in mind. Okay. The surface roughness is the second obvious. This can influence boundary layer flows, boundary layer flashback. It influences heat and mass transfer. It can enhance it. It can deteriorate it. It influences or can influence atomization and film stability. And the surface roughness typically enhances flashback risk because it can create a local hotspot somewhere. And also fuel coking, so especially of kerosenes or heating oils and so on. And this is particularly tricky when these tolerances and surface roughnesses influence the functionality. So because then it's difficult to reproduce the parts because the surface roughness and the tolerances are inherently somewhat stochastic due to the local powder size distribution that you currently have available when you melt the parts, right? You can't influence that. And then it becomes challenging to validate or compare numerical work with experimental data, because no part that you produce is alike if the surface roughness and tolerances affect the functionality. Yeah, for computational studies, I think it becomes tricky to compare under such conditions because you need to either resolve the wall, or you need to come up, or we need to develop, for example, data-driven models that can deal with the stochastic nature of this wall topology. One approach is to redesign the hardware to cope with these uncertainties a little bit better. Okay. The example I showed was this AM flex injector design that basically, despite the inaccuracies in the manufacturing, still delivered very good functionality in terms of atomization. Okay, coming to some key takeaways of this entire talk. I really think additive manufacturing, it unlocks design freedom, and the material combinations that it provides can be very exciting for combustion research from fundamental point of view, but also from component development point of view. So we use it to enhance fuel flexibility, to reduce non-CO2 emissions, but also to advance our fundamental understanding and innovate hardware that basically allow us to combine fuel flexibility and non-CO2 emission reductions. It can improve and also or deteriorate the accuracy of experimental data. And I think the most important thing here is to be aware of the uncertainties that you have and of their influence on the flow. Okay. Micro CT scans allow basically to reverse engineer the actual part to assure that you have the build quality and the part that you wanted, but also to mesh the real device and then to facilitate a numerical work. New challenges arise certainly from surface roughness and tolerances, opening up new fields in turbulent reacting multiphase flows or combustion in general. And it's very helpful to co-optimize the part you have with the AM process parameters, because then you can get much higher accuracy. With this, I would like to thank you for your attention. I gratefully acknowledge the funding by the DFG. Special thanks also to our AM project partner, the IFW at the University of Stuttgart, and the Institute of Combustion Technologies at the DLR Stuttgart, where we carried out the experimental work. And of course, my team, Yonsi Kang, Shiwan An, Basil Jose, and with Vicente Rubio, and all the students who have been involved, as well as the co-workers at the department Burner Systems and Diagnostics at DLR, in particular, John Pareja and Haisol Kim. With this, thank you very much for your attention. And I'm open to any questions.
Thank you. Thank you very much for this very interesting talk. Yeah, we can now open the Q&A session. So if anyone from the audience has a question to ask, please feel free to raise your hand or unmute yourself, whatever you prefer. Yeah, to break the ice, I will ask a question first.
Sure.
Regarding I didn't know about this laser technique to create for additive manufacturing. I was in my mind it was just the deposition of a material. If I see a 3D printer, that I guess probably the most more common technique. So I was wondering, the fused deposition, fused material deposition, would it prevent inaccuracy that you see from the laser-based process, or it actually works to deposit the material like in 3D printer?
So the powder-based processes are typically quite accurate. This direct energy deposition, well, I'm just a user of additive manufacturing parts in the end. Like, I have been exposed to this a fair amount now, and so I try to answer this as best as I can. So direct energy deposition is quite a energy intense process as far as I know, and typically it's creating larger structures than the powder bed fusion. So here, the laser spot size for these powder bed fusion processes can be as low as like 30 micrometer, creating reasonably fine structures. I think the benefit of DED, so the direct energy deposition approaches, come when you combine it with conventional machining. So basically, you weld a part and then you directly machine it, and that can, of course, improve the situation under given circumstances. But when the parts get really small or the wall's really thin, I'm not sure how comfortable it is to machine like 100 micrometer thick wall. But yeah, so this talk predominantly focused on powder bed fusion processes. Okay. With direct energy deposition, I have not had a part that could achieve these accuracies. Last year I was at the Form Next exhibition, and I think Nikon was developing some micro DED process where they could achieve sizes of like a few hundred micrometers, if I recall correct.
Okay, thank you. Are there questions from the audience? Okay, in the meantime, I'll take the opportunity to ask another question. Regarding the injector that you showed us, I guess you call it the space field injector.
Yeah.
Yeah. What would be the head loss if we have to, due to the presence of the orifice? Would it be also a challenge to scale up those kind of injector in industrial?
Yeah. We actually measured the pressure loss across these. In particular, when we have the, hang on, I have a backup slide for that. That's one backup slide I have.
Quite good.
We estimated the injection area here. So we have a normal tube to supply the fuel that has a cross-section area of 0.3, so 3.1 times 10 to the power of -6 square meter. When we use the space filling injection system with porous caps, the normal area actually increases. And we have seen this in pressure loss experiments as well. The pressure loss to the fuel is not really a problem. We can easily handle this. So here you see these porous tips basically on these microtubes printed on, and that I think we had like for jet velocity, bulk jet velocity of 120 meter per second with fuel-rich conditions for hydrogen, we had a pressure loss to the fuel system of, I think it was 2 bar or so. It's like nothing crazy. And this is basically worst case scenario, right? Like typically you don't run this rich, and this was at reasonably high flow velocities. Yeah, the bigger problem is, but we haven't optimized for that as well, to be honest, was we have to flow the air around this injection system, right? In comparison to flowing around the plain tube here. And the pressure loss to the air was a bit higher, but again, not optimized for that. I think we had 300 millibar to the air pressure, roughly what we had loss on a not optimized system, and also the rather advantageous design of long combustor nozzles. But yeah, needs to be optimized.
Okay, thanks. And just maybe I missed it, But how do you enhance ammonia cracking with these injectors? It's for because of enhanced mixing, or there are other?
Yeah. So at the moment, we blend the fuels upstream. It's synthetic cracking. There is this project, this overall project, we strive to do in situ cracking. So the material we use for printing is Inconel, Inconel 718, and the one of the motivations for the project is to produce a material that is catalytically active towards ammonia at high temperatures. And that basically the idea is to fuel ammonia and then crack ammonia into hydrogen and nitrogen in a few additively manufactured fuel reformer that is then placed into the burner in the end. But for now, it's still synthetically created mixtures that follow like stimulating cracking, ammonia cracking, basically. So we have ammonia, nitrogen, hydrogen in a mixture. If that makes sense.
Yeah. Okay. If there are no questions from the audience,
can you hear me?
Please, yes.
Yeah, Chinonso here. I'm joining from the UK. I'd like to find out, to print a complete nozzle, how long does it take?
That's very much dependent on the build height. So the build height, the layer height, and the height of the part is basically driving this process. So I give you an example. Sorry, so my computer is kind of slow. So here we have a height of 30 millimeters, roughly. The build time. We have a layer height. We operate because we want to have high accuracy. We have a layer height of 20 micrometer, and the processing time is 6-7 hours. It's not so bad. And you don't create one, right? You basically pack the entire build platform with parts that you want. So we usually have, like, our build plate holds I think 19. We can fit 19 injectors on that, and then in 7 hours we have 19 different designs. So the problem is actually not the printing process time. The problem is that you have so many parts then that want to be tested.
Okay.
That's the thing that really is costly in time.
Yeah, nice. Thank you for the presentation as well. I think I should have started with that. For the in situ cracked ammonia, how efficient was that process? Do you get so much ammonia passing through, or do you crack a significant amount?
Still under development. This is a matter of residence time and temperature predominantly. And also the actual Inconel you use. So different Inconel materials have different catalytic activity towards ammonia. So far, all the tests. So these in the end, hopefully we will receive a reformer that is working for us. The catalytic part is being done at the TU Berlin in this project. So far, they have tested various powders and also additively manufactured parts, basically. It's a residence time game. If the residence time is long enough, you achieve reasonably high conversion efficiencies. But they reached like 60-70% already without optimizing this fully.
Okay.
But it's still ongoing investigations. As I said before, the ammonia, the cracked ammonia flames that we investigated is all still synthetically generated fuel mixtures so far. Hopefully, in a year from now, I can tell you more precisely how this really behaves in a real combustor. Yeah.
Sure. Thank you.
Pleasure.
Okay, very good. I think we can close the the session here and free our speaker, whom I thank very much for this talk. And yeah, I hope to see you all very soon for the next appointment of this lecture series. Thank you very much, Fabian.
Thank you very much for the opportunity. Speak
Have
to
a
you
nice
soon.
weekend.
Thanks.
Yeah,
Same to
see
you.
you.
Bye.
Bye.